Okay, we move to the second and last talk of this session, which is by Giovanni Scala on self-testing tilted strategies.
Good afternoon to everyone. I'm happy to be here, and I would like to thank the organizer as well as my collaborators and affiliated institution listed on the screen. So could you really trust a quantum device just because a company tells you it's quantum? Self-testing is the way to find out. It certifies the state and the measurement of an untrusted quantum device just by looking at the correlation that we observe without really know the internal description of the device or believe the manufacturer. And this is crucial for device-independent QKD as it ensures the users their device genuinely generate quantum correlation without be expert how the devices are built. So everything boils down in the probability that yesterday Jeff and Mate Jeff and Mate yesterday was explained to us, and if there exists a unique quantum realization consisting on the state and the observable, then self-testing works. And in this talk, we will see that's the case for two ideal detectors, one inefficient one and two noisy ones. So the real question is when we can say we self-test a quantum device. So let us look at the CHSH scenario in this space-time cartoon. So Alice and Bob receive a photo from the shared state psi, and in their black box laboratory far apart from each other, and they also select by pressing a button their observable. Let's say in the cartoon both press the red button, and if a psi is maximally entangled, they will observe perfectly correlations. So in the cartoon both the left lamps are turned on. So and by repeating this many times, they will be able to produce these statistics, the behaviors, but only 8 are the independent numbers, and we can parameterize them by the local correlators, the 4 local correlators and the 4 joint correlators. So self-testing is then a retrodictive task such that from the output probability from the experiment, or equivalently from this set of correlators that maximally violate a given Bell inequality, we work backwards to identify what was the quantum realization that reproduced the observed statistics. So the condition when self-testing works is basically when we maximally violate the Bell inequality. So let's see this in the CHSH inequality, here written both in terms of correlators, in terms of probability, and the maximal quantum value is the well-known Sirelson bound. Here is where the magic happens, because once we observe the Sirelson bound, this allows us to write the shifted CHSH operator, and then we can express it in the form of SOS decomposition. So the key point is exactly this one. When the correlation allows us to observe the 2 root of 2, then the SOS form implies some relation between the observable on the state psi. And with a little bit of algebra, this is isomorphic to the Pauli algebra with the maximally entangled state, the singlet state. And this is how we self-test in this case. But of course, truth of 2 is never observed in the real experiment. So the question is, can we still self-test in the presence of imperfect detectors? The self-testing condition is asking the following question. Which quantum strategy yield the maximum loophole-free non-locality in the presence of inefficient detector? Let us look together this cartoon, where the blue region is the set of quantum correlation lie between the local and non-signaling polytope. And the optimal strategy is this point P0 on the boundary of the quantum set that is at the maximal distance from the local polytope, identified by this blue straight line, which is the CHSH, that it works when eta, the efficiency of the detector, is 1. But when the efficiency drops below 1, P0 is no longer the distance at the is no longer the point at the maximal distance, but it is this purple point P. So therefore, we need to write the shifted operator based on P. Or on the other way, we can still work with P0, but we need to tilt the Bell inequality. And this idea was worked out in the paper of PRA of 2015, where beta alpha is the tilted Bell operator that takes into account the inefficiency of one detector. And the nice part here is that even this operator, allow the sum square decomposition. So you see that the Einstein bound, I'm joking, the Bell local bound is 2 plus alpha, and the quantum optimal value is this root of 8 plus 2 alpha square. And thanks to the SOS decomposition, we can express in terms of PI, where these are polynomial operators. And again, when we observe the optimal quantum value, easily we can self-test, and we obtain the self-tested realization psi in terms of single angle theta, as Jeff yesterday was mentioning, and also the Alice settings mi. Both theta and mi are related by the tilted parameter alpha, as you can see on the left. So now, can we generalize towards a more realistic scenario when 2 detectors are inefficient? So the operator we introduce is the doubly-tilted CHSH. The local bound is 2 plus alpha plus beta, and the tilted parameter alpha and beta are related with the inefficiency of the detectors eta A, eta B from this relation. And the region of interest is alpha plus beta lies between 0 and 2, where this bound comes from the geometry of the local and no signaling polytope in the case of 2 input, 2 output scenario, which is the scenario that allows us to work in the Jordan's lemma. And thanks to the Jordan's lemma, we can expect to self-test state and observable of this kind. So the role of self-testing now is reduced to explicitly determine for each optimal quantum value. Here I call it C, Q, alpha, and beta, the function of the cosine theta A, theta B for the settings, and the Schmidt coefficient S0 for each alpha and beta. So naturally, can we follow the same path of the previous 2 cases? So can we looking for the SOS decomposition of this Bell operator? And because there exists a one-to-one correspondence between the SOS decomposition and the MPA hierarchy introduced yesterday by the talk by Jeff, we can start to chart how large must be the family of operators where we can indeed observe this decomposition. And the plot on the left shows that by approaching the critical limit, alpha plus beta going to 2, neither the hierarchy L equal 10 achieve the wanted convergence. You can see that this we cannot have a convergence on the plot on the right. But for alpha or beta on this axis, then is enough the level 1 plus AB to obtain the sum square decomposition, as we saw in the previous slide. So we cannot follow the same path, and a new idea should be introduced. So again, thanks to the Jordan's lemma, without assuming any dimension of the Hilbert space, we can work on these 4x4 operators, and the solution I will provide just for alpha equal to beta, but can be easily extended for alpha different than beta. So the idea is the following. The maximal quantum value is the largest root of the largest eigenvalues of this operator. So how we find the eigenvalues, we calculate the associated polynomial, and being a root of the polynomial, impose the first condition q equals 0. And q equals 0 is an implicit function in lambda, where the variable are the cosine CA for Alice and Bob, CB, that also needs to be maximized because we want to find the optimal settings of the Alice and Bob. So this also introduces another condition. So formally, the Lagrangian of this optimization problem is in equation 3. I will rewrite it on the top of this slide. And now I can proceed with the standard Lagrangian multiplier optimization. So this will define a system of equations in the variables lambda, CA, CB, and S, where S is the Lagrangian multiplier. And this defines a ring such that can be solved with a standard routine in algebra, which is the Grobner basis elimination procedure. How basically works this routine? You want to eliminate, for example, the variable S, CA, and CB, and the routine will output a polynomial f of lambda. So the largest root will provide the optimal quantum value, and rather than eliminating, for example, CA, we eliminate lambda, we will obtain another polynomial, GA, to compute the optimal cosine of theta A. Similarly for the Bob settings. I will show you the result directly of this solution. So equation 6 is the polynomial f of lambda. The root I didn't display for saving space on the slide. Then I compute also the polynomial GA and GB that for alpha equal to beta, they coincide. And the maximal root is in equation 7, depending only on the tilted parameter alpha. And finally, for self-testing the state, once I calculate the optimal cosine, I plug back to the operator, check if the maximal quantum value is non-degenerate, and the related eigenvector will be my optimal quantum state. These are the results for alpha, the analytical result for alpha different than beta. These two plots say the same thing, the optimal quantum value on the left in terms of tilted parameter alpha and beta, on the right in terms of the inefficiency. And you see that for alpha and beta 0, we obtain the serial sum bound, and when we go towards the critical limit, the local bound saturate the quantum 1, and there is no room to self-test quantum correlation. And the same can be visualized in the right plot, where below the red-blue line, the detectors are too noisy. This is the result for the optimal settings. The observation here is that by approaching the critical limit, the settings, the observable gets aligned closely to commuting. And finally, the last is the optimal state. On the left, we plot the 4 eigenvalues of the operator. The orange one is visibly non-degenerate, so it exists the unique eigenvector, where I plot on the right the Schmidt coefficient. And you see that for alpha and beta 0, we have the maximally entangled state as S0 S1 equal to 1 by root of 2. And by approaching the critical limit, the state became separable. So to put it in one sentence, in two input to output scenario, we can always uniquely characterize the quantum realization that attains the observed quantum correlation produced by a untrusted noise device. Thank you for your attention.
Any questions?
Thank you for the nice talk. I have a curiosity about the slide in which you show the state and the operator that you are certifying back. Here. So it seems that when let's say the efficiency goes to 1, you are not going to the CHSH observable and state, right? So why, how you can certify such operator in that case?
No. When the efficiency of the detector goes to 1, alpha and beta goes to 0. You see that the equation 1 gives you exactly the Bell operator, the standard, the CHSH operator.
Yes.
So the thing here is that I'm not saying in this slide what is the value of theta A, theta B. That's why maybe you can
No, because A0 and B0 are sigma Z, both of them, right? So I don't understand what. So this is not what happened in standard CHSH device independent, no?
But
typically one is tilted, is sigma Z plus sigma X over square root of 2.
Yeah, maybe, this was supposed to be.
Okay, maybe also this is rotated.
Yes,
here.
yes.
Okay, thank you.
Okay, then if there are no more questions, let us thank the speaker once again.